Hello everyone. In the previous lecture, we have been studying some of the subgroups of the group GL2R or maybe GLNR in general. One of them was this orthogonal group, and then we looked at the group GLNC. There we introduced the subgroup SUN and so on, and we studied some of the other some properties of the subgroups that we have been dealing with. For instance, that this group of special orthogonal matrices has got index 2 inside this group of orthogonal matrices, and here we also observe that SUN has got infinite index inside UN. Today we will focus on uh, on the orthogonal matrices, on the orthogonal group, and we will try to see how do the elements of this orthogonal group relates to some of the symmetries that we observe in in our daily life. So we'll try to focus ourselves within Rn. Sometimes we'll also focus within R2 or R3. To be able to visualize some of the results that we will be discussing, it's a good idea. It will be a good idea to keep the examples of two-dimensional plane, namely R2, and this example of three-dimensional space R3 in mind. So start with this notion of isometry. So what is an isometry? Before getting into that, let's recall this notion of Rn first. So this Rn consists of this kind of n tuples. We usually write them in a write them vertically. So these are the column vectors. This is the n tuples written in the form of column vectors. Okay, so this is Rn. You know that it comes with this notion of addition. One can scale the elements of Rn by real numbers and so on. This Rn, this space, is equipped with a nice structure which is known as the dot product, or sometimes it is also known as the inner product. So it takes two elements of Rn, that is two column vectors consisting of n coordinates as the entries, uh, and determines their product or defines their product as follows. So given two elements x1 up to xn and y1 to yn of Rn, we send them this pair to x1 y1 plus x2 y2 plus xn yn. So we multiply the coordinates and add the product. So what we get is known as the dot product of these two vectors lying inside Rn. One can also write down this real number in the matrix form. So if you if you call this column vector as x and call this y, then recall that x and y are just column vectors. So if you want to put x horizontally, okay, and put y vertically, then the product of these two is precisely this real number. In other words, the dot product between x and y is precisely x transpose y, the product of these two matrices, x transpose and y. Okay, one can note that this dot product induces a notion of distance on Rn. In fact, given two vectors, or rather given two elements xy inside Rn, their distance is denoted by this xy between two vertical lines. So the distance, this is read as distance between this is read as the norm of x minus y, but whatever it is, the distance is denoted by this symbol, and this is the square root of the dot product of the inner product between x minus y, uh, the square root of the inner product of x minus y with itself. Okay, one can check that this is a non-negative number. So for instance, if these two vectors are equal, then all these terms are greater or equal to 0. So this quantity is non-negative, and then one can take the square root, so it's well defined. Okay, anyway, so with all these notations, okay, maybe let me make one remark. So here you can check that this coincides with the usual notion of distance that you are familiar with within R2 and within R3. Okay, so if you take two vectors x1 x2 and y1 y2 within R2, then you can check that this is precisely the distance, or at least the way you know the distance between those 2 points. This coincides with that notion of distance. Okay, and now it will be important to focus on the maps from Rn to Rn, okay, which preserve this distance, okay, for any two vectors or any two elements xy lying inside Rn. By that I mean we will be interested in maps from Rn to Rn, such that if we are given two elements xy from Rn, then the distance between x and y will be no different from the distance between mx and my, and this should hold for all xy inside Rn. In such a situation, we say that this map preserves distance, okay, or we'll call it isometry, or we'll say that this is a rigid motion. So we say that M preserves, or maybe I should write it in this form. We should say that M preserves distance. Okay, great. It will be good to have some examples of isometries or rigid motions. This kind of maps are also called rigid motions. Okay, roughly speaking, you can also call them distance preserving maps on Rn. It is clear geometrically or intuitively that translation maps are isometries or rigid motions, in the sense that they preserve distance. That is, this equality holds for all xy inside Rn. Okay, this is something that one can check. Indeed, if you look at if you consider a translation map from Rn to Rn, maybe translation by an element b, then this is an isometry, for the reason that if you look at x, the distance between x and y, or rather maybe we first focus on x minus y, then one can check that x minus y coincides with the images, the difference of the images of x and y under this translation by b map. Okay, and so it follows that the translation by b map is an isometry for any b inside Rn. Okay, and some further minor observations, but they are quite crucial. For instance, if we have two isometries, two distance preserving maps m1 and m2 from Rn to Rn, then if you look at their composition, that composition also turns out to be an isometry of Rn, as can be verified from the steps, because if you look at the distance between the image of x and y under the map m1 composed m2, okay, then you are measuring the distance between the images of these 2 points m2x and m2y under the map m1. Okay, since m1 is distance preserving, so this quantity coincides with the distance between m2x and m2y, and since m2 is distance preserving, it follows that this quantity is equal to the distance between x minus y. So this is equal to this quantity. So it follows that the composition of two isometries is an isometry of Rn. Okay, great. So in this proposition, we will try to have certain equivalent formulations of the notion of rigid motions, that is, the notion of distance preserving maps. More precisely, we will focus on the distance preserving maps that fixes the origin. Okay, so if we start with a map M, and then we'll have bunch of equivalent formulations for the notion of a rigid motion that fixes the origin. Okay, so let me go through this condition first. The first one is that, anyway, this proposition says that the following statements are equivalent. Okay, so the first one is that M is a rigid motion fixing the origin. Okay, and the next one is that M preserves the dot product. That is, if you take two vectors x and y, compute the dot product, that will coincide with the dot product of mx and my. Okay, and this should hold for any xy inside Rn. And another equivalent formulation is that M is the left multiplication by an orthogonal matrix. M is the map which is left multiplication by an orthogonal matrix. That is, there is some n by n orthogonal matrix A such that mx is equal to ax for any x inside Rn. Okay, so let's try to establish the equivalence of at least some of these statements. So let's first assume that this very first condition holds, that M is a rigid motion fixing the origin. Okay, so suppose M is a rigid motion that fixes the origin, then of course we know that these two quantities are the same. Why? Because M preserves distance. Okay, so we have that this condition holds for all xy inside Rn. Okay, and here of course we can substitute y equal to 0, and if you substitute y equal to 0, then we know that my is equal to 0, because you have started with a distance preserving map that fixes the origin. So my, and y, all these four quantities, they disappear from here, because we are subtracting 0. So you have mx and mx here. So the dot product between mx and mx coincides with the dot product between x and x. Okay, so you have established at least a part of this statement. So here note that you have to show the dot product between mx and my has to be same as the dot product between x and y for any xy. So rather we have shown that the dot product between mx and mx is same as the dot product between x and x. Okay, but from this statement itself, one can establish this fact. One can establish this fact by an elementary observation. Okay, so let's see. So if you look at this equation, okay, then you can expand using the property that dot product is linear in both the coordinates. Okay, using that one can show that this quantity is equal to the dot product between mx and mx minus twice this quantity, the dot product between mx and my. So here you're using two facts, that dot product is additive in each of the coordinates and that it is commutative in these two coordinates. By that I mean that dot product between x y is same as between the dot product between y and x. Okay, so one can check that this quantity is no different from this one, and the quantity on the right hand side is equal to this. Okay, and then since we know that mx, the dot product between mx and mx with itself is same as the dot product between dot product of x with itself for any x inside Rn, so these two quantities they match and these two quantities they match. So we obtain that the dot product between mx and my is same as the dot product between x and y for any xy inside Rn. So here we used an elementary, how to say, maybe one can call it a trick, but this is very useful. Okay, great. So it means that we have established the second criterion, assuming that the first statement holds. Okay, so now let's assume that I think the third criterion. Okay, let's assume that m is left multiplication by an orthogonal matrix. Okay, then we have that mx equal to ax for any x inside Rn. Just the statement itself means just this. Okay, and then one can check that the square of this quantity. Okay, the crucial step lies here. This dot product can be expressed as the transpose of the first vector times the second vector, and here if you take transpose and the order gets swapped, here you have a times x minus y. If you take the transpose, you obtain x minus y transpose times a transpose, and from here also you can take a out, so that you get a times x minus y, and these two all together, that gives you the identity matrix, the n by n identity matrix, and that implies that the square of this quantity is same as the square of the distance between x and y, and that shows that m is a rigid motion. Okay, it shows that m is a rigid motion, and from the fact that mx equal to ax, you also know that it fixes the origin. Okay, so assuming that m is left multiplication by an orthogonal matrix, one can show that m is a rigid motion fixing the origin. In other words, one could show that the third criterion implies the first one. Okay, we were supposed to prove the equivalence of all these three statements. We have showed that 1 implies 2, we have showed that 3 implies 1, we now need to show that 2 implies 3. Okay, so let's discuss that. To show that 2 implies 3, first we prove that the identity map from Rn to Rn is the only map that preserves the dot product and fixes the basis vector even up to en. Okay, so here ei's are the standard vectors. Okay, the standard basis vectors. By that I mean e1 is 1 and then sequence of n minus 1 zeros, e2 is 0 comma 1 and then n minus 2 zeros, and so on. More generally, ei is the element of Rn whose ith coordinate is equal to 1 and the rest of the coordinates are 0. Okay, first we show that if you look at a map from Rn to Rn that preserves the dot product and fixes the basis vectors, then this has to be the identity map. Okay, suppose if from Rn to Rn preserves the dot product and fixes these basis vectors even up to en, then what we know is that, at least as a consequence, this holds, right? And since we have assumed that the basis vectors are fixed, okay, we know that f of ei is same as ei. So what you know is that the dot product between fx and ei is equal to the dot product between x and ei. Okay, so it follows that the ith coordinate of these two vectors, fx and x, they are the same. So we obtain that fx equal to x. Okay, thus we establish this very first statement that the identity map from Rn to Rn is the only map satisfying, or rather preserving, the dot product and fixing the basis vectors. Okay, and now let's try to show that 2 implies 3. To show that so the statement 2 says that m preserves dot product. So let's move ahead with that hypothesis. We assume that m preserves the dot product. Okay, so it immediately follows that all these vectors are orthonormal. Why? Because the inner product between these two, m ei and m ej, is same as the inner product between ei and ej. So that is 1 and 0 according as I is equal to j or I not equal to j. Okay. So now you look at the matrix whose ith column is equal to m ei. Okay, And now since we know that these vectors m(v1), m(e2) till m of en, all these vectors, there's an orthonormal set, it follows immediately that it follows immediately that the matrix A is an orthogonal matrix. Okay. And it also follows that A inverse, or rather you can observe that A inverse is an orthogonal matrix, because inverse of an orthogonal matrix is an orthogonal matrix. Okay, so you know that A inverse is an orthogonal matrix. Now you also know that 3 implies 1. So you know that left multiplication by A inverse, this map, is a rigid motion. Okay. So now if you look at this composition of these two maps, this left multiplication by A map, this map composed with the rigid motion that, composing the map M that you have started with, A inverse composed with M. Okay, here by A inverse I mean left multiplication by A inverse from Rn to Rn. There is a rigid motion that we know, and this being composition of two rigid motions has to be a rigid motion. Okay, and since we know that M preserves dot product, M of 0 has to be 0. Why? Because the dot product between M of 0 with itself has to be 0. It follows that M of 0 is 0. So by now we have established that A inverse M is a rigid motion that fixes the origin. We have already established that A inverse M is a rigid motion. We have shown that M fixes the origin, and A inverse, this denotes left multiplication by an orthogonal matrix. So A inverse M, this also fixes the origin. So thus we have obtained a rigid motion fixing the origin, and since we know that 1 implies 2, that is, a rigid motion fixing the origin has to be of this shape. Okay, since we know that 1 implies 2, so we know that A inverse M, it preserves the dot product. Okay, and now also observe that by the very construction of the matrix A, the rigid motion A inverse M, it preserves all these basis vectors e1, e2 up to en. So we have established that A inverse M A inverse M preserves dot product, and it fixes the basis vectors e1 up to em. And earlier we just observed that a function or any map from Rn to Rn satisfying these two criterions, that has to be the identity map. So it follows that A inverse M is the identity map on Rn. So M, the map itself, the map that you have started with, and assuming that you have assumed about the map M that it preserves the dot product, that M has to be the left multiplication by A map. Okay, and where A is orthogonal as observed before. So we established that 2 implies 3. Okay, great. So we have obtained certain equivalent criterions for the rigid motions of Rn that fixes the origin. Okay, great. And now we are going to show that if you look at any rigid motion, okay, from Rn to Rn, okay, then this rigid motion is of the following form. So this is Ax times b, that is the rigid motion M applied to an element x of Rn is equal to Ax plus b for some n by n orthogonal matrix A and for some element b inside Rn. In other words, this is the composition of the translation by B map and the left multiplication by A map. So you take a vector x, you first left multiply by A, and then you translate it by B for some B. Okay, this A and B depends only on the rigid motion M that you have started with. Okay, this is essentially straightforward. Why? If you rely on the previous proposition, then you know that if you have a rigid motion that fixes the origin, then it has to be of this shape, that is mx equal to ax for some orthogonal matrix A. Okay, and this has to hold for any x inside Rn. And here the rigid motion that we have started with, we do not know whether it fixes the origin or not, but you can you can somehow modify M suitably so that you end up getting a rigid motion of Rn that fixes the origin. So how to do that? You first look at the image of the origin under the rigid motion M that you have started with. Okay, let's denote the image of the origin under the rigid motion M by B. And now if you look at the composition of these two rigid motions M and the translation by minus B, okay, you can show that it fixes the origin, and of course being the composition of two rigid motions has to be a rigid motion. Thus you have obtained a rigid motion of Rn fixing the origin, and by what we have just discussed, namely the previous proposition, we know that this composition has to be left multiplication by A map. where A is an orthogonal matrix, an n by n orthogonal matrix. So from that we obtain the criterion for, or the classification for, all the rigid motions of Rn. That is, any such rigid motion has to be of this form. Okay, great. And now as a corollary we can establish the following, or we obtain the following. If you have any rigid motion m from Rn to Rn, it admits an inverse. So first of all, it is not clear from the definition of rigid motion that a rigid motion from Rn to Rn has to be surjective. This is not clear. But thanks to, if you use theorem 271, then of course it is clear that it is a bijection from Rn to Rn. Okay, thus it admits an inverse from Rn to Rn, and this inverse is also a rigid motion. Okay, so maybe you can have two different, although equivalent, but apparently two different approaches to prove this. So let me just let me follow one of them. You know by the previous result that if you start with a rigid motion from Rn to Rn, it has to be of this form. Okay, and now if you look at this map which sends x to A inverse x minus A inverse b, then one can check that both the compositions are equal to the identity map on Rn. Okay, and that proves the result. Okay, that any rigid motion admits an inverse, and its inverse itself is a rigid motion. Okay, great. So thanks to what you have discussed, we have been discussing about rigid motions. It follows that the set of rigid motions of R2 forms a group under composition of functions that's denoted by M. Okay, so earlier you have already showed that, rather you have observed that composition of two rigid motions is a rigid motion. Okay, and associativity and all that, that follows. Okay, because composition of functions is associative. Okay, and the closure property, the first property that is to check is that the closure property follows. In other words, the composition of two rigid motions is a rigid motion. That's immediate. The associativity property follows because composition of functions is associative, and then we have to go for existence of an quote-unquote identity element. Okay, of course the identity map from R2 to R2 does the job. And for inverses, for the very last condition that we have in the definition of a group, we are done by corollary 272. Okay, great. So the group of rigid motions of R2, the set of rigid motions of R2 that forms a group under composition of functions, and we denote it by this symbol M. Okay, and from now on we are going to study the finite subgroups of M. Okay, that is the subgroups of M containing finitely many elements only. So before having a detailed or at least somewhat satisfactory study of this finite subgroups of M, it is good to have an example of certain finite subgroups of M. For instance, if you look at this matrix, one knows that this is an orthogonal matrix, or one can verify it immediately that this is an orthogonal matrix. Okay, it's a 2 by 2 orthogonal matrix. This is an element of O sub 2, the group of 2 by 2 orthogonal matrices, and one can check that this map, okay, that x going to row 2n times x, okay, that is the product of these two matrices. Here row 2n denotes this matrix. Okay, this is a rigid motion of the plane. Okay, thus this map M that we have just defined, that is an element of M. Okay, so here M stands for the group of rigid motions of R2, the group of rigid motions of R2. Okay, sometime for simplicity we'll rather prefer to use the notation row 2n, okay, for this map M itself. Okay, whereas row 2n was just a matrix. Okay, thus the subgroup of M generated by this left multiplication by this matrix is a finite subgroup. Okay, as one can immediately observe, because this as a matrix has got order n. Okay, and one can also look at the dihedral group D2n. Okay, there is a subgroup of GL2R generated by these two elements. That is, this is the smallest subgroup of GL2R that contains these two elements. Okay, and now one can define each element of D2n can be realized as an isometry of the plane. Namely, you send a vector x to A times x. Okay, one can observe that for any element A inside D2n, it defines an isometry of R2. Okay, and so we have to each element of D2n, each element D2n we have an associated isometry, that is isometry of R2, that is an element of M. Okay, now if we identify each element of D2n with the associated element of M, then it allows us to consider the dihedral group as a subgroup of M. Okay, in other words, the map that we have defined from D2n to M by sending an element A of D2n to this rigid motion, to this isometry of R2, okay, this map that we have just defined from D2n to M, okay, so this defines an injective group homomorphism, okay, and thus as an application of the first isomorphism theorem, one knows that this D2n has to be isomorphic to its image, being because this map, that this group homomorphism that we have defined, that is an injective map. Great. So if you look at the finite subgroups of M, maybe we start with the finite subgroup G of M, then it turns out that any such subgroup has a fixed point. That is, there is a point P inside R2 that is fixed by every element of G. Okay, this is clear for the previous examples that we have just considered in example 273 and 274. Okay, if you want to find out this point P in the context of these two examples, you can just look at the origin. Okay, so origin does the job, but in general, if you start with any finite subgroup G of M, then you really do not know, okay, what could that P be. But the point is that one can show the existence of such a point P. Okay, this is fairly straightforward, and but the technique is quite useful. Okay, this gets used over and over again in various other contexts in apparently different form. Okay, let's try to go through. Let me introduce certain terminology. If you have a finite subset of the plane S1 S2 Sn, then their average, that is S1, that is 1 over n times S1 plus S2 plus Sn, this is called the center of gravity of this set. Okay, and now if we have a rigid motion M of the plane, and we denote the images of all these points S1 up to Sn and the image of P by adding a prime next to them. So the image of S1 S2 Sn is denoted by S1 prime S2 prime till Sn prime, and the image of P is denoted by P prime. Then one can check that this P prime is equal to the average of these points S1 prime S2 prime till Sn prime. Okay, so what does this try to say? This says that if we take a finite subset of the plane and look at its center of gravity, okay, then whatever rigid motion that you may take, that will send the center of gravity, that namely the point P, to a point, okay, that will be the center of gravity of the images of these points Si. Okay, in other words, rigid motion sends this given a finite subset of the plane, okay, or rigid motion sends its center of gravity to the center of gravity of the images of the points that you have started with. Okay, great. So how do you go about it? So we use the criterion that, or the theorem that you have just established, that if you start with a rigid motion, then it is of this shape, that mx equal to ax plus b for some 2 by 2 orthogonal matrix A. Okay, and from that it immediately follows that P prime is equal to the center of gravity of the points S1 prime till Sn prime. So how does it follow? Because P prime is by definition image of the point P, this has to be of the form AB plus BP by the definition of the matrices A, this n by n matrix A, and the n by 1 matrix B. Okay, so it is of the form AP plus B, and then from a straightforward computation, it follows that this is equal to 1 over n times S1 prime till Sn prime, that is the center of gravity of the set of points S1 prime till Sn prime. Great. So we have proved that a rigid motion sends the center of gravity of a set of points to the center of gravity of the images of these points. Okay, and we'll use this property to establish some interesting result, namely that this theorem that we have stated a while ago, that if you take a finite subgroup, then there exists a point P inside R2 which is fixed by every element of G. Okay, as you might guess from this proposition, that we are going to apply some quote-unquote averaging technique. Okay, so let's see. So we fix a point S of R2, and on the other hand, we enumerate the elements of G as M1, M2 up to Mn. Okay, and now look at the image of this point S of R2 under this elements of G. This G is a finite subgroup of M, right? So let's denote the images, okay, by convention. Of course, we know that the images are denoted by M1s and then M2s till Mns. Okay, these are the images of this point S1 up to Sn under under the elements of the finite subgroup G. Okay, we claim that okay, rather we call, sorry, maybe I just maybe said something wrong. I meant that these points m1s, m2s up till mns, these are the images of this element s under this elements m1 up to mn of this finite subgroup G. Okay, we denote these points by s1, s2, sn for brevity. We claim that the center of gravity of these points, that is the images of this chosen point under the images of G, okay, that is that is a fixed point for any element of G. Okay, so if we apply any element of G to the center of gravity of this point, then that will be fixed. Okay, why is that so? Okay, we'll explain in a moment. So let's use a shorthand for center of gravity of this set. Let's denote the center of gravity by P. Okay, now let mi be an element of G. You know that mi is a rigid motion. Okay, so mi sends the map, it sends the center of gravity P of S1 to the center of gravity of the image of S1 up to Sn under this map mi. Okay, so that is the center of gravity P of S1 to Sn is sent to the center of gravity of the set mi applied to S1, mi applied to S2, and then till mi applied to Sn. Okay, now what is mi applied to S1? It is mi applied to m1 of S, and then mi applied to m2 of S, all the way till mi applied to mn of S. Okay, so here you are looking at the center of gravity of this set. So you are looking at the image, we are looking at the images of this point S under the maps m1 circle mi composed with m1, mi composed with m2 till mi composed with mn. But if you look at these elements of the group G, then you know that this list of elements is is equal to m1 m2 is equal to m1 m2 mn in some order by the left cancellation law. Okay, so here what you have is precisely this set. Okay, this m1s, m2s till mns. Okay, so you have this set s1 up to sn, and here you are looking at the center of gravity. So what you have established is that, or rather observed, is that the center of gravity of this point, of this set of points s1 up to sn, is sent to itself by mi for any element mi of G. Okay, so any element okay, so here of course, as I just mentioned, we are using the left multiplication law, and that this map is surjective. Okay, that the fact that G is finite. Okay, that's why this map from G to G, which sends an element to mi composed G, this is a bijective map. Its injectivity is clear from left multiplication, and surjectivity is clear. Surjectivity is clear from the fact that the group G that we are discussing is finite. We have started with a finite subgroup. We have started with a finite subgroup G of the group M. Great. So it follows that the center of gravity P of S1 up to Sn is sent to P itself by any element mi of G. Okay, so it knows. So we have just established that the point P is a fixed point for all the elements of G. Okay, so this proves this nice result, this fixed point theorem. There are several other fixed point theorems that one learns and that one learns in mathematics in several other contexts. So any theorem that says that there is some point that is fixed, at least in some sense, by certain, under certain actions in some sense, then that theorem is usually become familiar as fixed point theorem in that context. Okay, so this is one of the first instances of fixed point theorems. One of the first instances of a fixed point theorem that probably one learns in the context of study of symmetry of the two-dimensional plane R2. Anyway, and now let me just make some remarks about certain finite subgroups. Okay. So as you know by this theorem that given any finite subgroup of the group of rigid motions of the plane M, we know that there is a fixed point. Okay, and to describe a finite subgroup G of M, first we pick a fixed point. Okay, and we set the origin at that point only. Okay, in other words, we may assume that G is a finite subgroup of the subgroup O of M that consists of the isometries of R2 which fixes the origin. Okay, note that this from this finite subgroup, whatever finite subgroup that we may start with, we will end up obtaining a fixed point, and we can place the origin at that point. Okay, and then we know that we can realize G as a subgroup of this group O, okay, and this group O is defined as a subgroup of M that consists of the isometries which fixes the origin, okay. And now again from O2 to O we have a nice map that sends a 2 by 2 orthogonal matrix that is an element of O2 to O, okay, which is the left multiplication by A map on R2, okay. And by the results that we have discussed, it follows that this map from O2 to O is an isomorphism, okay, because if we look at an element of O, that is an isometry, there is an isometry of M that fixes the origin, okay. There is an isometry of O that fixes the origin, so it has to be left multiplication by an orthogonal matrix, okay. Thus we know that this map is surjective, and of course this map is injective too, and one can check that this is the group homomorphism, okay. So this shows that it shows that this map that we have just been discussing is an isomorphism, okay. And this allows us to consider the subgroups of O2 as subgroups of O. For instance, this matrix lies inside O2, and the group that is the group that it generates, if we denote it by Cn, then Cn can be thought of as a subgroup of O, okay. And also these two matrices that generate the subgroup D2n, okay. And now one can identify D2n with a subgroup of this group O, which is the subgroup of M consisting of the origin fixing isometries of R2, okay. In fact, one can show the following, that if you take a finite subgroup of O, then G is equal to one of the following. G is equal to the cyclic group Cn of order n, or G is equal to the dihedral group D2n of order 2n, okay. So the examples of the finite subgroups of O that we have studied here, that you have observed here, and the first instance where we have studied it, this in these two examples, in these two consecutive examples, sorry, I think I went past. Okay, yeah, right here in example 273 and in example 274, okay. These two are all the examples when we are concerned with the finite subgroups of O, okay. Great. And with the statement of this theorem we conclude this lecture.